In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about permanent magnet. A magnet is a material or object that produces a magnetic field. This magnetic field is invisible but is responsible for the most notable property of a magnet, a force that pulls on other ferromagnetic materials such as iron, steel, nickel, cobalt, and etc., and attracts or repels other magnets. A permanent magnet is an object made from a material that is magnetized and creates its own persistent magnetic field. An everyday example is a refrigerator magnet used to hold notes on a refrigerator door. Materials that can be magnetized, which are also the ones that are strongly attracted to a magnet, are called ferromagnetic or ferrimagnetic. These include the elements iron, nickel, and cobalt, and their alloys. Some alloys of rare earth metals and some naturally occurring minerals such as lodestone, ferromagnetic, and ferrimagnetic materials are the only ones attracted to a magnet strongly enough to commonly considered magnetic. All other substances respond weakly to a magnetic field by one of several other types of magnetism. Ferromagnetic materials can be divided into magnetically soft materials like annealed iron, which can be magnetized but don't tend to stay magnetized, and magnetically hard materials, which do. Permanent magnets are made from hard ferromagnetic materials such as alinoc and ferrite that are subjected to special processing in a strong magnetic field during manufacture to align their internal microcrystalline structure, making them very hard to demagnetize. To demagnetize a saturated magnet, a certain magnetic field must be applied, and this threshold depends on coercivity of the respective materials. Hard materials have high coercivity, whereas soft materials have low coercivity. The overall strength of a magnet is measured by its magnetic moment, or alternatively, the total magnetic flux it produces. The local strength of magnetism in a material is measured by its magnetization. An electromagnet is made from a coil of wire what acts as a magnet when an electric current passes through it, but stops being a magnet when the current stops. Often, the coil is wrapped around a core of soft ferromagnetic material such as mild steel, which greatly enhances the magnetic field produced by coil. Discovery and development. History of electromagnetic theory. Um, Ancient people learned about magnetism from lodestones or magnetite, which are naturally magnetized pieces of iron, and the word magnet was adopted in Middle English from Latin magnetium, lodestone, ultimately from Greek means from Magnesia, a place in Anatolia where lodestone were found. Today, Manisa in modern day Turkey. Lodestones suspended so they could turn were the first magnetic compasses. The earliest known surviving descriptions of magnets and their properties are from Anatolia, India, and China around 2500 years ago. The properties of lodestones and their affinity for iron were written of Pliny the Elder in his Encyclopedia Naturae Historia in the 1st century AD. In 11th century China it was discovered that quenching red-hot iron that was aligned with the Earth's magnetic field would leave the iron permanently magnetized. This led to the development of the navigational compass as described in Dreampool essays in 1088. By the 12th century to 13th centuries AD, magnetic compasses were used in navigation in China, Europe, and Arabian Peninsula and elsewhere. A straight iron magnet tends to demagnetize itself by its own magnetic field. To overcome this, the horseshoe magnet was invented by Daniel Bernoulli in 1743. A horseshoe magnet avoids demagnetization by returning the magnetic field lines to the opposite pole. In 1820, Hans Christian Ørsted discovered that a compass needle is deflected by a nearby electric current. In the same year, Andre Marie Ampere showed that iron can be magnetized by inserting it in an electrically fed solenoid. This led William Sturgeon to develop an iron core electromagnetic in 1824. Joseph Henry further developed the electromagnetic into a commercial product in 1830 and 1831, giving people access to strong magnetic fields for the first time. In 1831, he built an ore separator with an electromagnetic capable of lifting 750 pounds or 340 kilograms. Physics magnetic field. The magnetic flux density, also called magnetic B field or just magnetic field, usually denoted by B letter. It is a vector field, and the magnetic B field vector at a given point in a space is specified by two properties. The first is its direction, which is along the orientation of compass needle. The second one is its magnitude, also called strength, which is proportional to how strongly the compass needle orients along that direction. In SI units, the strength of the magnetic B field is given in Tesla. Magnetic moment. A magnet's magnetic moment, also called magnetic dipole moment and usually denoted micro, is a vector that characterizes the magnet's overall magnetic properties. For a bar magnet, the direction of the magnetic moment points from the magnet's south pole to its north pole, and the magnitude relates to how strong and how far apart these poles are. In SI units, the magnetic moment is specified in terms of ampere multiplied by square meter, ampere times meters square. A magnet both produces its own magnetic field and responds to magnetic fields. The strength of the magnetic field it produces is at any given point proportional to the magnitude of its magnetic moment. In addition, when the magnet is put into an external magnetic field produced by a different source, it is subject to a torque tending to orient the magnetic moment parallel to the field. The amount of this torque is proportional both to the magnetic moment and the external field. A magnet may also be subject to a force driving it in one direction or another, according to the positions and orientations of the magnet and source. If the field is uniform in a space, the magnet is subject to no net force, although it is subject to a torque. A wire in the shape of a circle with area A and carrying current I has a magnetic moment of magnitude equal to I as a current to as ampere, and multiplied by area as a meter square. And the chapter of magnetization. The magnetization of a magnetized material is the local value of its magnetic moment per unit volume, usually denoted m, which units ampere divided by meter. It is a vector field rather than just a vector like the magnetic moment, because different areas in a magnet can be magnetized with different directions and strengths. For example, because of domains, a good bar magnet may have a magnetic moment of a magnitude zero point 0.1 ampere times meter square and a volume of 1 uh, centimeter cubic, or 1 multiplied by 10 to the power of minus 6, and therefore an average magnetization magnitude is 100,000 ampere divided by meter. Iron can have a magnetization of around a million amperes per meter. Such a large value explains why iron magnets are so effective at producing magnetic field. Modeling magnets. Two different models exist for magnets: magnetic poles and atomic currents. Although for many purposes it is convenient to think of a magnet as having distinct north and south magnetic poles, the concept of poles shouldn't be taken literally. It is merely a way of referring to the two different ends of a magnet. The magnet does not have distinct north or south particles on opposing sides. If a bar magnet is broken into two pieces in an attempt to separate the north and south poles, the result will be two bar magnets, each of which has both a north and south pole. However, a version of the magnetic pole approach is used by professional magnetization to design parameter magnets. In this approach, the divergence of the magnetization inside a magnet is treated as a distribution of a magnetic monopoles. This is a mathematical convenience and doesn't imply that there are actually monopoles in the magnet. If the magnetic pole distribution is known, then the pole model gives the magnetic field H. Outside the magnet, the field B is proportional to H, while inside the magnetization must be added to H. An extension of this method that allows for internal magnetic charges is used in theories of ferromagnetism. Another model is the ampere model, where all magnetization is due to the effect of microscopic or atomic circular bound currents, also called Amperian currents, throughout the material. For a uniformly magnetized cylindrical bar magnet, the net effect of the microscopic bound currents is to make the magnet behave as if there is a microscopic sheet of electric current following around the surface, with local flow direction normal to the cylinder axis. Microscopic currents in atoms inside the material are generally cancelled by current in neighboring atoms, so only the surface makes a net contribution. Shaving off the outer layer of a magnet will not destroy its magnetic field, but will leave a new surface of uncancelled currents from the circular currents throughout the material. The right-hand rule tells which direction positively charged current flows. However, current due to negatively charged electricity is far more prevalent in practice. Polarity. The north pole of a magnet is defined as the pole that, when the magnet is freely suspended, points towards the Earth's north magnetic pole in the Arctic. The magnetic and geographic poles don't coincide. Since opposite poles, north and south, attract, the north magnetic pole is actually the south pole of Earth's magnetic field. As a practical matter, to tell which pole of a magnet is north and which is south, it is not necessary to use the Earth's magnetic field at all. For example, one method would be to compare it to an electromagnetic whose poles can be identified by the right hand rule. The magnetic field lines of a magnet are considered by convention to emerge from the magnet's north pole and re-enter at the south pole. Magnetic materials. Magnetism, the term magnet is typically reversed for objects that produce their own persistent magnetic field even in the absence of an applied magnetic field. Only certain classes of materials can do this. Most materials, however, produce a magnetic field in response to an applied magnetic field, a phenomenon known as magnetism. There are several types of magnetism, and all materials exhibit at least one of them. The overall magnetic behavior of a material can vary widely depending on the structure of the material, particularly on its electron configuration. Several forms of magnetic behavior have been observed in different materials, including ferromagnetic and ferrimagnetic materials are the ones normally thought of as magnetic. They are attracted to a magnet strongly enough that the attraction can be felt. These materials are the only ones that can retain magnetization and become magnets. A common example is a traditional refrigerator magnet. Ferrimagnetic materials, which includes ferrites and the longest used and naturally occurring magnetic materials, magnetic and lodestone, are similar to but weaker than the ferromagnetics. The difference between ferro and ferrimagnetic materials is related to their microscopic structure, as explained in the magnetism. The next is paramagnetic substances, such as platinum, aluminum, and oxygen, are weakly attracted to either pole of a magnet. This attraction is hundreds of thousands of times weaker than that of ferromagnetic materials, so it can only be detected by using sensitive instruments or using extremely strong magnets. Magnetic ferrofluids, although they are made of tiny ferromagnetic particles suspended in liquid, are sometimes considered paramagnetic since they cannot be magnetized. Diamagnetic means repelled by both poles compared to a paramagnetic and ferromagnetic substances. Diamagnetic substances such as carbon, copper, water, and plastic are even more weakly repelled by a magnet. The permeability of a diamagnetic materials is less than the permeability of a vacuum. All substances not possessing one of the other types of magnetism are diamagnetic. This includes most substances. Also, force on a diamagnetic object from an ordinary magnet is far too weak to be felt, using extremely strong superconducting magnets. Diamagnetic objects such as pieces of lead and even mice can be levitated so they float in mid-air. Superconductors repel magnetic fields from their interior and are strongly diamagnetic. There are various other types of magnetism, such as spin-glass, super paramagnetism, super diamagnetism, and metamagnetism. And what about the shape? The shape of a permanent magnet has a large influence on its magnetic properties. When a magnet is magnetized, demagnetizing field will be created inside it. As the name suggests, the demagnetizing field will work to demagnetize the magnet, decreasing its magnetic properties. The strength of the demagnetizing field is proportional to the magnet's magnetization and shape, according to a specific equation. Here is called the magnetizing factor and has a different value depending on the magnet's shape. For example, if the magnet is a sphere, then the value of the demagnetizing factor also depends on the direction of the magnetization in relation to the magnet's shape. Since a sphere is symmetrical from all angles, the demagnetizing factor only has one value. But a magnet that is shaped like a long cylinder will yield to different demagnetizing factors depending on if it's magnetized parallel to a perpendicular to its length. Magnetic recording media (VHS) tapes contain a reel of magnetic tape. The information that makes up the video and sound is encoded on the magnetic coating on the tape. Common audio cassettes also rely on magnetic tape. Similarly, in computers, floppy disks and hard disks record data on a thin magnetic coating. The next one is credit, debit, and automatic teller machine cards. All of these cards have a magnetic strips on one side. This strip encodes the information to contact an individual's financial institution and connect with their account. Older types of televisions, a non-flat screen, and older large computer monitors, TV and computer screens containing a cathode ray tube employ an electromagnet to guide electrons to the screen. The next one is sensor. Permanent magnets are useful components for fabricating magnetic sensors for the detection of motion, displacement, position, and so forth. Speakers and microphones. Most speakers employ a permanent magnet and a current carrying coil to convert electric energy, the signal into the mechanical energy movement that creates a sound. The coil is wrapped around a bobbin attached to the speaker cone and carries the signal as changing current that interacts with the field of the permanent magnet. The voice coil feels a magnetic force and in response moves the cone and pressurizes the neighboring air, thus generating sound. Dynamic microphones employ the same concept but in reverse. A microphone has a diaphragm or membrane attached to a coil of wire. The coil rests inside a specially shaped magnet. When sound vibrates, the membrane the coil is vibrated as well as the coil moves through the magnetic field. A voltage is induced across the coil. This voltage drives a current in the wire that is characteristics of the original sound. Electric guitars use magnetic pickups to transduce the vibration of guitar strings into electric current that can then be amplified. This is different from the principle behind the speaker and dynamic microphone because the vibrations are sensed directly by the magnet and a diaphragm is not employed. The Hammond organ used a similar principle with rotating tone wheels instead of strings. Electric motors and generators. Some electric motors rely upon a combination of an electromagnetic and a permanent magnet. And much like loudspeakers, they convert electric energy into mechanical energy. A generator is the reverse. It converts mechanical energy into electric energy by moving a conductor through a magnetic field. This example and this simulation shows how to model the magnetic field surrounding a permanent magnet. It also computes the force with which it acts on a nearby iron rod. Thanks to symmetry of the geometry and the anti-symmetry of the magnetic field, only one force of the geometry needs to be modeled. On the antisymmetry plane, the magnetic field is perpendicular to the boundary. This condition is represented by a constant magnetic scalar potential. The model uses the zero magnetic scalar potential condition. If the air box is sufficiently large, the boundary condition used on its remaining exterior boundaries has little influence on the field in the vicinity of the magnet. Although an infinite element domain would give the very best results, this model uses the magnetic insulation condition for convenience. And here we are, there is a capsule simulation, and you see our geometry. This geometry, I make it more transparent. So you see It's half of the uh, our geometry, and we can make it as a double. You see the materials we have used is iron and nickel. This is the alloy of nickel and iron. It's a remnant flux density. The important things that we use is a recoil permeability, that how much holes there is to we can it's based on 1.05, and remnant flux density norm, and electric conductivity, and also relative permeability. And also for iron material you see that relative permeability, and also we have a specific sort of some other general properties, basic properties, and etc. We go through the magnetic fields as a physical module. The only physical module we have used is a magnetic field and no current. The all of the box and also the magnetic fields have been selected, and the equation we have used is, as I have described, is H is equal to minus delta Vm. And also we assume that the delta B is equal to 0. And we see the three-dimensional plot group. Is a flux density, magnetic flux density norm. You see in our pole we have a more and higher magnetic field. And thank you so much for watching my tutorial video until the end. And also you can download this console simulation from github.com/mathscript.